All right, good morning. This is Mr. Thill coming to you again with some kitchen science. So our topic in class this week is chemical reactions, specifically chemical reactions and how they are different from physical reactions, but also how they're similar to physical reactions. So just to review your learning from last week, when you have a chemical or physical reaction, you're mixing two things together. It could be two different pieces of matter, two different liquids, a liquid and a solid. Basically, you're mixing two things together. Now, in a physical reaction, all that really happens is that the two materials combine. They don't make anything new. They just kind of mix together. So the weight on the mixture should stay the same. In a chemical reaction, you'll see certain indicators that a chemical reaction is occurring. I have a list of those right here to review. So for chemical reactions, you're going to see maybe a change in temperature, a change in color. Now, when I say change in color, I mean like a weird change in color. It's not like putting red food coloring into water. You know the water's going to turn red, but you're not making anything new. It's more of an unexpected change in color. Like if you added bean juice to an acid, you'll get a weird pink color. Other indicators of chemical reactions are a noticeable smell. If it makes a solid when you mix two liquids together, if you see solid particles form, or if you see bubbles. So what I have here today is an example of a chemical reaction for you, one that covers the second and third indicators of chemical reactions, and that is a rotting piece of fruit. So you can see here that this nectarine, which was left out and exposed to air for about 2 weeks, has definite signs of change of color. The nectarine itself is reddish-orange, but when you expose it to air for a long period of time, you end up with this kind of white and green stuff growing on it. If you know anything about food cycles, that's an example of a decomposer, right? But it's also an indicator of a chemical reaction because you're seeing a color change that you don't quite expect. In addition, you can't smell it, but I can smell it. There's definitely be a noticeable smell or odor to this nectarine now that it's rotting. So this is a good example of a chemical reaction that occurs without you even thinking about it, rotting fruit. Other than that, you could say like rust on metal. That's a change in color that you don't expect. That's a chemical reaction as well. All right, so what we're going to do in a few seconds is we're going to take some different liquids and solids and mix them together and see what kind of reactions we get. And we're going to see like what's different between the reactions and what's the same. So we'll bring that to you in a couple of seconds. All right, so I'm back, and now we're ready to begin our mixtures of our solids and liquids to see what kind of reactions happen. So just remember that even if you're having a chemical reaction, the mass of the two materials should not change, okay? Like even if you see bubbling or an explosion, if you're able to gather all the stuff back together, you're not going to see a new mass. So we're going to be mixing together salts and water, and I'm going to be mixing together baking soda and vinegar. One of these mixtures will not produce a chemical reaction. All you're going to see is that the solid dissolves into the liquid. The other one, you will definitely see a chemical reaction. You're going to see an indication of bubbles or a temperature change to show that something new is being made. So we're going to start with the non-chemical reaction first. So for that, we're going to take our salt here. I'm going to weigh it for you. So right now the salt with the container is about 6 ounces. And we're going to mix in about 1 ounce of water. Now my kitchen scale is not perfectly accurate, so we might be off by 1/10 of an ounce or so when we mix the things together, but you're not going to see a really large weight gain or weight loss. We should see when we mix our ounce of water into our salt that we have about 7 ounces of material total inside our container. So here's our ounce of water. I'm going to go ahead and pour it in now. And you can see, looking at the scale there, that we have 7 ounces as our measurement. And even if I mix it in to dissolve it, you're not going to see the weight change by a lot. You might see a bit of a change because there might be some matter left on the spoon, but the overall weight, once I let it settle, should be about 7 ounces. And there you go. We have a measurement of 7 ounces. So even though you can't technically see the salt, we're not gaining or losing any matter. We're just having the same matter look different. So we don't see a color change. The temperature has not changed at all either. There's no weird smell that I'm not expecting. We don't have a new precipitate or solid forming. What we see is that the salt we added in is kind of falling to the bottom, but that's not new, so it's not a chemical reaction. And there's definitely no bubbles. And while the water got like a little cloudier, that's not a weird change in color. If you add a white solid to a clear liquid, you're going to see some cloudiness result. So this is definitely not an example of a chemical reaction or chemical change. It's an example of a physical change where you dissolve salt in water. So if I were to taste this, which I don't want to do because it's going to be really salty, it'll just taste like salt water. So that is one example of mixing things together in a physical reaction where we don't have any actual change in the materials. We just end up with water and salt combined. All right. But as you saw, we didn't lose any salt. It stayed in the water. It's just now part of the water. Okay. Now for our next combination, we're going to be mixing together our apple cider vinegar and our baking soda. So let me go ahead and show you the weight of the baking soda. Let me clean off the container first so we don't have any extra water weight added to it. Turn on my scale. So the baking soda in the container weighs about, let me zero this out real quick. There we go. Weighs about 5.9 ounces. Okay? So when I add the apple cider vinegar here, you're going to see a reaction. But the weight should settle at about 6.9, 7 ounces after the reaction occurs. There is some gas produced, so you might see a little bit of change in weight because the gas will escape up into the air. I won't be able to capture it. But I'm probably going to try to cover it up as best I can so we lose as little of the material as possible. So let's go ahead and do our combination of an ounce of baking soda of apple cider vinegar with our baking soda. All right, and if you watch, you'll see a chemical reaction occurring. All right, so there it goes. Right now it's 7. We're about to lose some of it because it's going to go over the edge, but it's 7 ounces. So nothing new occurred here. It's just the same amount of stuff, just looks different. The bubbles are a definite indicator of a chemical reaction, but our mass is staying at 7. So even though we had like a little mini explosion here and it produced CO2 bubbles, the mass of the apple cider vinegar and the baking soda did not change. It stayed the same. So even though we made a new chemical, carbon dioxide, we did not change the weight of the two things we mixed together. So while we do have a chemical reaction here, because we're seeing a formation of bubbles, and there is a smell too, it's not actually adding any weight or losing any weight. So I hope that proves to you that no matter what you're mixing together, as long as you can capture the stuff you're mixing, like when it explodes or pulls out, you're not going to add or lose any matter. You're not going to add or lose any weight. All right, so there you go, chemical reactions.